back, hopefully. Let's see. I don't know if it's the same link, is it? Copy. Check, check, check. Is it a different link? Different link. Okay. Hello, hello. I'm going to use it. Chat working again. All right. All right, so definitely getting some questions here. We'll see, we'll get people back in the chat. Let me email the link. Okay, back up and running. Just waiting for people to get here. Okay, 38A and 33B, 36B, 38C. Okay, yep, absolutely. Just wait for people to get back. Okay, so Julia and Amelie just sent me some questions, but I want to make sure people get back on the live stream. We are back, ready to go. The chat seems to be working again, and I did get a couple email questions. So again, I just want to wait a couple of seconds here, let people get back in. Okay, so let's go over 14. So we're going to do 33, 36B, 38A, and 38C for right now. Okay, so let's get into that. So was it 33B? Okay. So 33B. So when you so all these questions, we're just analyzing the data. Okay, so I don't have a copy of the table, so hopefully you have your copy of the book with you so you can check it out. So if you have any questions about, I think you're good with A. It said B in your email. All right, so just calculating the rate constant and including the units. So that's kind of what we're just going over, how to get the units. So let's understand how we're going to get our units, right? So notice that in the chart, the initial rate was like the rate given was always molarity per second in that chart. And I think it's molarity per second for all these charts right here in this section of the textbook. So our unit of time is going to be seconds. All right. And we figured out that both reactants were first order based on the data. So that means the reaction order is 2. And so what we're going to do is the units for K would be 1 over molarity raised to the second power minus 1. So the raised to the reaction order, which is 2 minus 1. So 2 minus 1 is 1. So it's 1 over molarity raised to the first power times seconds. That's how we get our units for K. Okay. But then how do we get the value for K? All we have to do is plug in one of the sets of data. Okay. So we have our rate law. So we figured out our rate law. Now what I did was I plugged in the values for trial 1. So this was the molarity of the hypochlorite ion. This was the molarity of the iodide ion. And this was what the rate was equal to. Right? So you just plug those numbers in and solve for K. And maybe I think I did my math right. Maybe I didn't though. But it comes out to be 60.4. And again, how do we get the units? We do 1 over molarity raised to the reaction order minus 1. The reaction order is 2 here, so 1 over molarity, and then also times seconds on the denominator, okay? So that's 33b. So anytime you have to calculate the rate constant, you just have to plug in one set of data from one of the trials and solve. And then, just make sure you follow that equation that went over, right? So, this is up here. This is what the units for K will always be equal to. Okay, this is this right here. Okay. Okay, so you said 36b as well. So let's go to that one. Okay, so again, what are the units for K? That's what 36b is asking for, right? What is the, B, what are the units for the rate constant? So again, look at what we found. We found NO is second ordered and oxygen is first ordered. So what does that mean? That means the reaction is third ordered. So if we go to our units of K, it's going to be 1 over molarity raised to 3 minus 1. So 1 over molarity squared, and then times the unit of time. And again, for all these, our unit of time was seconds. So that's how I get my units for K. Okay? And then 38A and C. So let's go to 38 and C. Okay, so yeah, 38A is definitely it's a little bit difficult. And the reason why it's difficult is they give us, let's see, it's going to be easier if I just go ahead and type it, okay, up here. Okay, so let's do this. Let's do a chart. Table. Let's do insert a table. Come on. Why isn't it? Oh, you can't insert a table. Okay. 1, 2, 3. Okay. So we got the S2O8 minus here, or 2 minus. 2 minus. And we got the I minus here, okay, and 0.018, 0.036, 0.027, oops, 0.036. So I know you can look at the, so if you have your book out, please have it open to this chart because I'm not going to fill in the whole thing. I just want to have the molarity numbers here so you can see it, okay? So the reason why this is kind of a tricky one is because there's no two trials where the S2O8 concentration remains constant, okay? But there are two trials where the I minus stays constant. So what we can do is, since there's two trials where the I minus stays constant, right? Trials 1 and 2, we can definitely know the order of this reactant, the S2O8 2 minus ion. Okay. All right. So we're going to do that. So what I do in this case is I always take so I take the larger concentration and divide it by the lower concentration. So I'm going to do trial 2 divided by trial 1. So 0.027 divided by 0.018, right? That's 1.5. So the concentration from this trial to this trial increased by a factor of 1.5, right? And then do the same thing to the rate, but again, I'm doing trial 2 divided by trial 1. So the 3.9 times 10 to the negative 6 divided by 2.6, and that also equals 1.5. So the concentration changed by a factor of 1.5, and the rate changed by a factor of 1.5. So that means since whatever changed to the concentration, the same thing happened to the rate for this, that means it's first order. Okay, so I know this is first order. All right, so that's how we got this part. Okay, that's how we know that for sure. Okay. However, the I minus is a little tricky. We have to figure it out now, knowing that S2O8 is a first order reactant. So think about this, right? If I double S2O8, the rate should double. But if I double this and I also change the I minus, the rate is going to double because of the S2O8 change, because I know what I did to that and I know it's first ordered. But then any other change has to be attributed to what I did to the I minus. Does that make sense? All right, so let me show you what I mean, okay? So what you would do is pick two trials where they both change, right? So let's just go trials 2 and 3. Let's compare 2 and 3. Okay, let's compare 2 and 3 to each other. Okay, so we're comparing these two trials. Let's look at what the change is. What is the change for the S2O8 2 minus ion? We would do 0.036 divided by 0.027, right? So the change for the S2O8 2 minus ion changed by a factor of 1.333. Okay, so let's think about this, right? And I also changed I minus, right? So let's go to the rate. If we figured out the rate only increased by a factor of 1.33, that means whatever change I did to I minus had no effect, because I know if the rate only changes by this, then what caused the rate to change by that factor? That increase, because I know this is first order, okay? But I come back to here, but if the rate does anything else besides increase by a factor of 1.33, that has to be attributed to this change, okay? So let's go look at what the change is for I minus. So if we do 0.054 divided by 0.036, that gives us 1.5. So the I minus changed by a factor of 1.5. So let's go over the different scenarios right now. So if rate changes by factor of 1.33, then we know I minus is zero order. Okay. What else could it be? What if I minus was first order? Well, then that means the rate is going to increase by a factor of 1.33 and a factor of 1.5. So, 1.333 times 1.5. So, if they're both first order reactants, if the rate, so if you take 1.33 and multiply it by 1.55, you get 1.9995. Okay, so if the rate increases by a factor of close to 2, right, a factor of 1.9995, close to 2, then you know that I minus is also first order. Okay. Well, what's 1.5 squared? 1.5 squared is 2.25. So let's say I minus was second ordered. That means whatever change you do to the concentration, that change squared is what happens to rate. If I minus is second ordered and we increased the concentration by a factor of 1.5, then the rate should increase by a factor of 2.25, which is 1.5 squared, right? But it would be 2.2, but for this problem, it would be 2.25 times 1.33, because we also changed the concentration of that of this first order reactant. So that would be what the rate does just by the change in concentration of I minus if it's second order. But then on top of that, we'd have to multiply. So 2.25 times 1.33, the rate would have to increase by a factor of 2.99, so basically 3. Okay? So what did the rate do? Okay, so if the rate only increased, so what I'm going to do is we were comparing trials 2 and 3. So if what I'm going to do is I'm going to take the rate from trial 3 and divide it by the rate of trial 2. And if it comes out to be this number, then I know I minus is zero ordered. If it comes out to be this number, then I know I minus is first order. If it comes out to be this number, then I know I minus is second order. And this is all predicated on the fact that we figured out what this ion's concentration was. Okay, so let's do that. We're going to take 7.8 times 10 to the negative 6 and divide it by 3.9 times 10 to the negative 6, and that comes out to be 2. All right, so right there, boom, this number. Okay, so what does that mean? It means I minus is also first order, and so that's how we got I minus being first order. Now that's going to be kind of the trickiest type of question you'll see, is if you don't have a trial, or you don't have two trials to compare where one of the reactants concentration is held constant within those trials. Because if it's not held constant, then you really have to know what the other reactant is before you can figure out the order of the other reactant. Okay? So hopefully that makes sense. And okay. And then let's see, and then 38C was also asked about. Okay. Okay, so remember, if you look at the reaction, and I want to fix this. Okay, so we got S2O8 2 minus plus 3I minus yields 2SO4 2 minus 2 sulfates plus I3 minus. Okay, so here's the deal, right? For every one of these I'm losing 3 of these. So the I minus is going to decrease 3 times. The rate of disappearance for I minus is going to be 3 times faster than the rate of disappearance for this ion, because it's a 1-to-3 ratio in which you lose it. Okay, so if you know the rate of disappearance of one thing, then all you have to do is multiply by the mole ratio to get the rate of disappearance for the other reactant, or to get the rate of appearance for any of the products. Okay, does that make sense? So the rate of S2O8 2 minus is going to be 3 times slower than the rate of I minus. I minus is 3 times faster because you're losing 3 I minuses for every one of these ions. Okay? All right. Okay, so hopefully that answered those questions. And let me know if you still have more questions on those. Email me or put it in the chat. Let's see, I got another question here. 36C, D, and E. Okay, so let's go back up to there. Okay, so all you had to do for 36D, we had to calculate K for each of the trials. So all we're doing is, here's our rate law. Okay, Maddie, this is our rate law. And so all we're doing is taking the data from each trial one at a time. So trial 1, we're plugging in, the molarity of the NO from trial 1, the molarity of oxygen from trial 1, and the rate from trial 1, and solving for K. And we end up with that number, and I round to 3 sig digs each time here. So for trial 1, it came out to K came out to be that value. For trial 2, it came out to be the same value, but for trial 3, it came out to be that value. But if I take the average of these numbers and round to just 3 sig figs, it comes out to be that value. You know, if you're not worried about sig digs, obviously it's not going to be exactly this, but that's what it's asking. It's just asking you to calculate the average. You're not going to. I've never seen an actual AP question where they ask you to calculate the average K value. It's always if they ask you to calculate the K value, it's always all you have to do is take one of the trials, the data from one of the trials, plug it in, and solve for the K value. Okay. Now again, make sure you know how to get the units of K. Okay. And then D. What are we doing? So now, okay. So okay. So this kind of goes back to knowing the mole ratio, okay? So the initial rate given in those charts is the initial rate of the reaction. It's the rate of the reaction. And so remember when, delta H, when you get the delta H value for a reaction, it's like delta H is like in kilojoules per mole of reaction. But if, the coefficient of one of your things is 5, you have to multiply by the delta H over 5 moles or 5 moles over the delta H, right? Like 1 mole of the reaction is equal to 1 times whatever the coefficient is of each thing in the reaction, okay? So what you're going to do is, if you want to, so now that we know the rate law, right? Now that we know what the rate law is, all we have to do is plug in the values given to us and solve for the rate. But that's the rate of the reaction. But if you look at the balanced equation, for every 1 time the reaction goes, right? So the reaction is this, 2NO plus O2 yields 2NO2, right? So every time the reaction goes, you lose 1 oxygen, but you lose 2 of these. So the rate of the reaction is equal to the rate of disappearance for oxygen because the coefficient's 1. But the rate of disappearance for NO is 2 times that amount, right? So what we did was we plugged in the values into the rate law once, because we know what the K value is, right? We figured out what the value for K is. Now we have the K value. We have the concentrations given to us. We plug those in. We solve for the rate. That's the rate of the overall reaction, but I have to know that for every 1 time the reaction goes, I lose 2 NOs. So the rate of disappearance of NO is going to be 2 times the rate of the overall reaction, okay? So you have to double that rate. So all right, and so if the coefficient was 3, you would have to triple the rate of the reaction, okay? If the coefficient's 1, then the rate of the reaction is the rate of disappearance for that reactant or the rate of the appearance for that product, okay? So again, notice that for E, we plug in our data into the rate law, but since the coefficient for oxygen is 1 in that reaction, the rate of the reaction is the rate of disappearance for oxygen, okay? So I hope that answers that question, okay? Let me know if you have any more. Okay. Again, if you have questions, please put it in the chat. Or, and I'll open it up to other questions besides the problem set. So, like, if there's anything else you want to discuss. So, this isn't for sure. I'm not 100% for sure. It's the email that I got from College Board is kind of iffy on it, but I think we're going to be able to allow you access to the secure items, but not necessarily have to use that secure browser anymore. So like all the practice tests that I was going to give you for our practice test assignment, where you guys were going to come meet me at the library or something to do practice tests, all that stuff, they uploaded those tests into Google Classroom. The only problem is you'd have to use the secure browser to access that, and you would only have access do a given amount of time. But I think based on the last email I read, and if I'm interpreting it right, because it's kind of iffy, I'm not sure. I think I'll be able to, just post those for you at some point so that you can just use them as practice. And I think that's how we're going to do our final exam eventually. Is I'm going to use one of those as the final. I think so. We'll see. But I think a lot of stuff is going to be in the AP Classroom. But again, we're still waiting for that April 3rd send out of what the actual AP exam will look like for you this year. So we kind of know how the questions are going to be asked, what it's going to look like, how intensive is it? You only got 45 minutes, so like how fast do you really have to work? And what I'm going to do when I get that on April 3rd is I'm just going to make a bunch of practice tests based on the practice questions they gave us, so that you guys can have those and just work on those, in the meantime. Because I think if I'm interpreting it right, your AP exam is only going to be free response, but I might end up just assigning a multiple choice final exam so that I don't have to grade any free responses selfishly. But we'll see. We'll talk about that when we get there. All right. Okay. Rate of disappearance and rate of appearance. Okay, so rate of appearance is usually so it's just how fast are you losing or gaining your product and reactant, right? Okay, so like again, let's look at this reaction here, right? If this is our reaction, what we need to understand is that as the reaction proceeds, as the reaction proceeds from left to right, I'm losing this and I'm gaining that. So they say rate of disappearance. They're saying the oxygen is disappearing, right, as this is appearing. But you're going to lose the oxygen slower than this appears, right? Does that make sense? So like it's based on the mole ratio. So like every time the reaction goes, I lose one of these, but I lose two of these. So the rate in which this disappears is 2 times faster than the rate at which this disappears. Okay? And the rate at which this appears is equal to the rate that this disappears, because it's a 2 to 2, 1 to 1 ratio, right? Does that make sense? So like the rate in which this disappears equals the rate in which this appears. But if I know the rate at which this disappears and I want to know the rate of appearance for this, I got to double it. This disappears half at half the speed in which this appears, right? So let's take it. Let's say the rate of disappearance for oxygen is 0.50 molarity per second. Okay, like you were told. Okay, so what does that mean? It means you're losing that on average. You're losing that concentration of oxygen every second. The oxygen is decreasing by 0.5 molar every second. So if it started at 1, after a second, you're going to have 0.5, and after another second, you're not going to have anything left, right? That's not really what ends up happening. This is the average rate. It's not the instantaneous rate that's different, but right? So, but that's what it means. It means that's how much you're losing per second, right? Well, if I take 0.50 and I multiply it by my mole ratio, 2/1, right? That'll give me 1.0 molar per second, and this would be rate of disappearance for NO, right? So if I'm losing oxygen at a rate of 0.5 molar per second times 2, right, times 2/1 is how fast I'm losing the NO, okay? And then also times 2/1, right? 1.0 molar per second would be rate of appearance for NO2. Okay, so that's what we mean. Like, so it's rate of appearance for products because products are being produced, they're being formed, and it's rate of disappearance for reactants because they start the reaction and then they get consumed. Okay. All right. All right. So, are there any other questions? Okay. Any other questions? Okay. I'm just checking my email, waiting for the chat. Any other questions? Any other questions not related to the problem set? Any other questions from anything else? Chemistry related, school related? What do you got? If you don't have any questions, just let me know. We've been given the green light to reach out to you, even though I've kind of been reaching out to you before. Been given the green light, so let's just not talk about that. But so you should be hearing from your other teachers if you haven't soon. And again, we'll be able to start making things mandatory, being able to grade things, that kind of thing. And what I think I'm going to end up doing is you will still have assessments. I still got to assign you grades and stuff. But once it's mandatory, once I can make all especially the unit stuff, the unit 7 stuff mandatory, you'll get a quiz on that. It'll maybe be like a Google Classroom quiz or something, or it might be just a quiz on AP Classroom or something like that. Is so yeah. But what again? I kind of I'm anxious. I want us to do it now, but we have next week, and then we have spring break, and then we have so I can't really do anything like that until the 14th of April. Okay. How was K value found in 34B? 34B. Let's see. I plugged in. I plugged in the data from one of the trials, probably from trial 1. I'm guessing. So it would end up being 0.06 squared times 0.03, and then whatever that is, and then take the rate 0.0248 and divide it by whatever that ends up being, and that's how you get the K value. So again, so 0.06 squared, oops, 0.06 squared times 0.03, and then at 0.0248 divided by whatever that came out to be, 1.08 times 10 to the negative 4. And it comes out to be, in your calculator, 229.629, so rounded to 230 for 2 significant digits. But again, whenever you need to calculate a K value, it's just first we figured out a rate law. How do we know that's the rate law? We figured out the orders of the reactants. Now, once we have that, we can take the data from one of the trials. You plug in the rate, you plug in each concentration. Don't forget to square this one, and you solve for K. All right. So yeah, just take and you don't have to take it from trial 1. You could take it from trial 2 for trial 3. Just don't mix and match. I've seen some students where they take one of the concentrations from trial 1, they take another concentration from trial 2, and then they take the rate from trial 3. It doesn't work. Just take one of the trial's data, plug it in, and solve for the value of K. Okay. All right. question. So let's see. Oh, yep. Hey, good job, Amelie. You got it. That's a good correction. Notice you got to read, right? I just assumed it was rate of reaction. But they, if you read, so again, D and E, I'm wrong, right? My explanation is right if I was right about what I thought the initial rate was measuring. I thought it was just the initial rate of the reaction, but it's not the initial rate of the reaction. It's it's the rate of disappearance of NO. So the rate there in the chart in 46 in 36, the rate there in that chart is the rate of disappearance for NO. So when you plug in the data, that is the rate of disappearance for NO. Okay, so wait a minute. So sorry. When you plug it in, that is the rate of disappearance because the rates that we were finding was the rate of disappearance. So that should just be zero point 0.4. And then here is when we would do 0.4, but then we would have to divide by 2. Because again, what does this represent? This represents the rate of disappearance for NO, and for E, they're asking for the rate of disappearance for oxygen. And so you would have to take this and multiply by the mole ratio, which would be 1 over 2. Because again, what this represents is the rate of disappearance for NO. So that's a good call. Okay. The rates in that chart weren't the rate of the overall reaction. They were measuring the rate of disappearance of NO there. So that's why you don't have to double this one in part D. Okay, does that make sense? So yeah, it's just I didn't read the question fully. So lesson to be learned, read the question 100% and understand what's given there. I just assume, I kind of done these a lot, so I just kind of looked at the chart and read the question, and I just assumed it was the rates there was the rate of the overall reaction. Okay? So yeah, good catch. Okay. Amelie, did that answer your question? Like, do you understand why I was wrong on the answer key? Because the rates given in the table were the rate of disappearance of NO and not the rate of the overall reaction. Just making sure. Okay. Or I'm testing you. That's I guess that's always the go-to. I was testing you. I'm glad somebody caught it. Okay. So hopefully that got you. That makes more sense. Good catch. I'm glad you're on top of things like that. That's really good. Okay. Any other questions before we call it a day? Again, try to look at the book. So what you might want to do is kind of look at the new practice problems that I've assigned. Just read through them and go, okay, what? Like you maybe not have any idea, and then use kind of like then go and read. You don't need to sit there and read every single bit on every single page. There's only a few concepts that you need to get for reaction mechanisms. So you might want to like look what the kind of the questions are asking, and then go and look in that part of the textbook. Now, I'll answer the questions and I'll go over reaction mechanisms, but I'm kind of holding off on doing a full live stream on kind of like intro to mechanisms and stuff like that until we get to the 14th and so everyone can be there or is responsible for being there. In the meantime, you know, I'll sign the practice problems and stuff like that, and then I'll post the keys, and we can have question answer sessions, and it'll kind of be informal, me telling you how to do things versus kind of the formal me lecturing to tell you how to do things, because eventually we're going to have to do that again come the 14th. All right, good. All right, so I'm glad you got that. Thank you for catching that. Let me know if you have any other questions. And we'll call it a day if you don't. Okay. So I think also another thing, the county, make sure obviously you all are checking Blackboard, but make sure your friends know how to get into their Blackboard accounts, because I think what the county's going to have us do is something called Blackboard Collaborate Ultra or something. It's kind of like a meeting place, so where you'll get to I'll be able to hear your voice, and we'll be talking to each other. And if you want to, you can have your picture on the screen, or you don't have to use your camera or whatever, or you don't, and so we can kind of have a virtual meeting versus just I get the chat from you guys, but that's about it. And I think the county wants it done through Blackboard so they can monitor and make sure kids are showing up and they're where they're supposed to be at certain times, and that they're actually doing the work to gain the credit for the course. So that's what we're going to have training on that next week, and we're meeting as teachers to figure out what we need to cover and what we don't need to cover. So that's really more for my honors chemistry, because I have to, Dr. Hughes and I have to get together and figure out what exactly we want to cover and not cover. And we kind of have to be lockstep with that. But for you guys, since I'm the only AP chemistry teacher, I get to basically decide, but I'm letting College Board basically decide that. And, from now on, our focus should be, until you take, your focus really should be on, let's figure out what the AP exam looks like and figure out how you guys can, do your best on that. And then we'll figure out what we need to do for a final exam and that after we figure out what we're doing with the AP exam. You know what I mean? Okay. All right. So it doesn't look like there's other questions. I'm glad you caught that mistake on the key. And hopefully, if people watch the live stream later, to hopefully they'll understand that too. Again, read through about reaction mechanisms, try those practice problems, and we'll probably, it's really starting to look like I'll live stream Tuesday instead of Monday, because I have a bunch of different meetings on Monday, but I will let you know for sure Monday morning. I'll post something, and I'll post the key to those reaction mechanism problems. I'll post that on Blackboard when Sunday. I'll post that on Sunday, and but it looks like, I think you guys can probably, you might have access to all the answers too. I wish I brought the solutions manual so I didn't have to handwrite all the answers. I left those in my classroom. Didn't think of it. Anyway, have a great day. Thanks for joining me, and thanks for asking questions. I really appreciate you guys doing the work, even though it's optional, and I'm glad you guys are dedicated to do it. All right, so have a great rest of your Friday, and enjoy your weekend. Probably is not going to be much different than what your week was like. All right, so have a good one.